6.4, multiplying radical expressions. So I guess we've kind of seen a little bit of this already, just we were kind of separating things before. This leads into the real separations, which we're going to be seeing as well. So a couple things, right? If you see that you're multiplying, these bases don't have to be the same, but if the index is the same of the root or the radical that you're multiplying, then you can actually combine those into one individual multiplication problem. But with that skill, though, you can actually start with combined multiplication and then separate the two. So this is good because what you can do is, if you're going to simplify these, if you ever see they're not perfect squares or perfect sets, I guess we'll call them, then you can use kind of prime factorization to yank stuff out. Okay. Now, for the most part, we are dealing with squares, some cubes, and then they're going to throw some of the other indexes at us, usually like 4s and 5s. I don't remember seeing anything beyond that, but I could be wrong. Yeah, if you use prime factorization, every pair would be a perfect square, or every triple would be a perfect cube, if that makes sense. If it doesn't, that's okay. We're going to see some examples. But from those, that's what we're kind of splitting up here. So it says simplify the square root of 32, and it'd be nice to punch this into the calculator and get the decimal, which you could do. That's not what it wants. It wants it simplified, but it wants the exact answer, meaning we don't want the decimal. If you change a square root into a decimal, it's automatically rounded because those decimals go on forever without repeating or terminating. And so you can imagine how fun it would be to try to get to the end. So when it says simplify these, it's now saying it wants a square root in the answer. Now, if 32 was a perfect square, we would say, oh, it's just a number. But this one is not, right? We know the perfect squares from yesterday. We have them all memorized because that's what we do, and we love to memorize all those. But anyways, there's two ways to do this, so I'm going to show a couple ways. And then you kind of decide which way you like the best. I'm gonna use mostly the second way when we're dealing with square roots. So the first way, let's label this one so we know we're dealing with. So let me do it. This is prime factorization. Now, if you don't remember what prime factorization is, that's okay. But hopefully you'll remember soon how much you enjoyed it. So what we do is we take 32 and we just want two factors of 32. Doesn't really matter what they are. But we're trying to narrow or break everything down into its own prime factors. Now, we've been doing a lot of factoring, which is pretty much what we're talking about. A factor in a multiplication problem is a value that is being multiplied. In other words, 32, for example, you could, and I'm just using one set.
4 times 8.
4 times 8 would be one of them. Okay, now neither of those are prime though. Okay, which means you can break them up even further. If they were prime, we would circle them. So this is kind of like a prime factorization. Some people call it a prime factorization tree, and that's fine. But 4, for example, splits up into 2 and 2, both of which are prime. So we circle those. And then 8, I would split up into probably 2 and 4. You could say 4 and 2, it's the same thing, by the way. And then 4 splits up into 2 and 2, okay? So we end up with a bunch of factors here, 2s, all 2s right here, and that's okay. These are all prime factors of 32, meaning instead of writing this as the square root of 32, what I'm going to do is I'm going to write it now as the square root of 2 times 2 times 2 times 2 times 2. An exponent would work on this one. So I guess maybe I'll even do this 3 different ways. But from here, since we were looking at a square root, right, this means I need pairs. I need pairs, matching pairs, because matching pairs are perfect squares. All right, well, that's not hard to do. I see I've got 2 times 2, which would be 4, In fact, here's what I'm going to do. I'm going to do this with a lot more work than you'd probably ever want to do or use, but I'm going to use it anyways. So 2 times 2 right there, that would be the square root of 4. Now, do we know what the square root of 4 is? It's 2. Okay, so that's what we mean by if you find pairs here, you're looking at a perfect square. In fact, we have another set. These 2's right there, which is another, see if I can do this right, it's another square root of 4, which is 2. Well, the problem that we have right now is that this 2 does not have another 2 to pair with to make it a perfect square, which means that it stays on its own as its own square root of 2. So we write it in down here as part of our simplified form as a square root of 2. So this stuff right here that I just did, by splitting this up, that's kind of what that last slide was talking about, is once you get these factored out into what we're looking at is perfect squares in this case, you can separate those from the other factors, okay? So 2 times 2 is 4, 2 times 2 is 4. These ones just happen to be the same. They won't always. Now this would be pretty well simplified. It's almost finished, by the way. What we need is to multiply anything that can be multiplied, such as 2 and 2, which is 4. And then we'll just finish by multiplying that by the square root of 2. And this is our final answer right there, simplified. So I'm gonna use another method here. Some students really like prime factorization, and if that's you, don't worry about these other 2 methods. You can still watch, if you find that you like one of the others, then use it. But other than that, don't worry about it, okay? Because prime factorization will always work. Even if I don't use prime factorization in the way that I simplify them, but you like prime factorization, use it, okay? Now, the other way to do this, just like we've done with factoring trinomials, is you kind of look for a factor pair that works for, like you wanted the sum of the factor pairs to add up to the middle coefficient. We're kind of doing the same thing here, but we want to look at the factor pairs of these where one of the factors is a perfect square, because it usually is. And if that happens, if we find the biggest one, the biggest perfect square, then we just square root that and then we can be done. So here's what I mean, is let's just look at factor pairs of 32. Okay, so 1 and 32, we look at those. Is either of those a perfect square? Sure, 1 is. But this isn't really going to help us, right? I can just pull out a phantom 1 right there, and then that's good. So we don't actually ever look at 1 in the value we're looking at, kind of like we would with factoring trinomials. So we'll start in this case with 2 and, I'm going to do it like this, 2 and 16. Okay, so I know that 16 is a perfect square. How do I know that? Because I enjoy memorizing all of these math nerd facts, and so I just have it down. If you're not sure, just use the calculator, by the way. Now, let's say that you didn't notice that. Okay, so you may proceed and say, well, I know 32, and then you'd have 4 and 8. And 4 and 8, it's not divisible by 6 or 5 or 7. So that's actually all the factor pairs. And then you can see also that 4 is its own perfect square. Now, we don't want that set because 4 is not the biggest perfect square, 16 is, so we're not looking at that one. So in other words, I'm going to take 32, and I'm going to split it up into those 2 factor pairs, 16 and 2. Like this, because the square root of 16, I know, is 4. And then the square root of 2, that's not a perfect square, so we're just going to keep it there. That is done. And you notice that it's the same exact answer that we got here. This one does take a little bit more experience because you have to have your perfect squares memorized, right? 16 and 4. 4 would work. You could have the square root of 4 times 8, but it's not considered fully simplified because 8 can factor into another 4 and 2. So that I'm kind of using the prime factorization to show that. So you'd have to be careful with this method because if you don't find the right factor pair, then you may end up not having simplified it completely. So Now, to relate this to what we saw yesterday, I'm going to take 32 and kind of compare it to what we saw in yesterday's lessons. Geez, well, wasn't it 6.2 or 3? So 32 we could write as a exponent, right? That square root right there would be the power of 1/2. And that's not 32 times 1/2, of course. It's 32 to the power of 1/2, which is very different. But 32, just like we can see over here, it's really 2 to the power of 5, right? So here's what I can do is I can take 32 right here and make it, instead of 32, I can make it as 2 to the power of 5. And this would be to the power of 1/2. See, now I have exponents that I can multiply because of the parentheses, and then I end up with 2 to the power of 5/2. That's 5 times 1/2. Now, is that helpful? Perhaps. But what I would want is exponents that just really come out as 1, which would be, so I'm going to split this up, and this is where students start to hate this. It's like, oh, I can change it into 2 to the power of 5 over 2. That's great. We changed the base, and it feels good. But we're not finished. So 2 to the power of 5 over 2, I'm going to use more steps perhaps than you'd probably want to do. But that would be the same as 2 over 2 plus 2 over 2 plus 1 over 2. And then you'd have 2 to the power of 2 over 2 times 2 to the power of 2 over 2 times 2 to the power of 1 over 2. Oh, yeah, so some students are like, how the crap did you get that right there? So I have common denominators of 2, but I split 5 up into 2, 2, and 1. Why did I do 2 and 2? Because it matches the denominator. So that right now, that's what I'm going to do, is I'm going to take that, the 2 over 2's, which is really just 2 to the power of 1, and then I'm going to multiply that by another 2 to the power of 1, and then multiply that by the 2 to the power of 1/2. See, like this, a little bit more space.
This is the method that you use?
So,
I understand it, but I don't.
yeah, well, you can enjoy it someday. 2 to the power of 1 times, really it's just 2 times 2 is 4. See that? And then you got this 2 to the power of 1/2. Now I will change it back into a root so that it's in the format that the assignment wants. Boom. Now, yeah, you can see this way, it takes a lot of thought. Maybe you could say it takes a lot of experience. I don't know. You get to decide on your own. Like, you could have split this up over here. You could have taken that at that point, and then made it 2 to the power of 2 to the power of 2 times 2 to the power of 2 times 2, and then taking that to the 1/2. I'm not really encouraging this method right here, just because I think that takes a lot more experience than we have right now. But if you can, like if you can understand this from what we saw last time, then this may make a little bit more sense to you. I don't know. I prefer this method though. This is the one that I'm going to be using almost always. So again, if you like the prime factorization, that's good. If you want to just find the perfect squares, I should have labeled that. And then this one right here was just using the exponents. None of these are formal. Well, prime factorization is a formal method, but if you went to another teacher person or math nerd and said, why don't you use a finding perfect squares method, they'd be like, what the crap are you talking about? Because it's not a formal, as far as I know, it doesn't have a formal name to it. I could be wrong about that, being a math nerd, but I just don't remember that there is. There is a fourth method.
No.
It's my favorite method. It's called calculator method.
That's the fourth method.
Well, I'm still going to show it. I mean, it's called calculator method. It's a calculator method. Calculator. Let's see if I can spell that right. Calculator method. So here's what you're going to do. You're going to type in the square root of 32 and push enter. So, yeah, that's what you got to get the square root though, right? So that's the second. And then you're going to push, this is a square root, so you're going to push x squared. And then you type in 32. Then you push enter. And you'll never guess what the calculator gives you. It says 4 times the square root of 2. So I'm going to be using this method just so we can have some work. But this is a really nice way to at least check what you're doing, whether you're using prime factorization or finding the perfect squares or this exponent stuff. Calculator is at least a great way to check. Okay, so we're going to simplify this one. And again, the calculator will do this work for you, at least some of it. Not all of it, but some. And so what am I going to do? I'm going to take this 4 times the square root of 24 x to the power 5. And I'm going to find factors of 24 that I want the biggest perfect square, right? So you could say, again, don't use 1 as one of the factors, but 2 and 12, okay, that would work. Maybe you would want to use 8 and 3. Okay, that doesn't seem like it works. How about 4 and 6? That looks good. Are there any others? Nope. No, these are the only factor pairs. Of course, 1 and 24 works, but we don't want the 1. Now you'll notice right now I'm not even focused on the x to the power 5. I don't care about that. I would like if you didn't care about it yet. We're going to get there, just not yet, right? So I'm going to take that 4 and 6, and instead of writing 24, I'm going to write 24 as the square root of 4 times the square root of 6. Okay, and the reason I'm doing that is because the square root of 4 is a perfect square for 2. So then I have 2 times the square root of 6. What about this 4 in here in the front? This is not number 4 like the fourth problem. That's one of the factors in this problem. So we got to multiply that down here as well. Okay, well, what about that x to the power 5? Yeah, let's do that now. And yes, we'll deal with 4 times 2 here in a second as well. But instead of writing this as the square root of x to the power of 5, I'm going to write it. No, that's what I'm going to do. But instead of just x to the power of 5, I'm going to write this as x times x times x times x times x. And the reason I'm doing that is because now I'm kind of looking for, you could say, the prime factors. I'm looking for factor pairs. Pairs that match because they would be perfect squares, such as these two x's. Again, that's a perfect square for x. So the square root of x times x, I'll show that work. The square root of x times x is x. Okay, but I have another set. I got these two x's, right? So that would be the square root of those two x's, x times x, which you could write, for this one, let's take that back. Let's write that as x squared, just so you can see a different format for that. The square root of an x squared, remember, we saw this last time, but the square root and a exponent of 2 kind of undo each other, and then you're left with just that x. Now that last x we have is the square root of x because there's no other x's to pair this last x with, so we got to keep that by itself. And I know that x times x is x squared, and then we still got that multiplied by the square root of that purple x. So this is in 2 parts right now. Let's combine them, because that's really what we want here. So anything on the outside of the square root needs to stay on the outside. And we'll do, right here, we'll do 4 times 2, which is 8. Okay, now I'm going to take this x squared and then multiply it by the 8 there. And then the square root, we have the square root of 6 and the square root of x, which I'm going to combine into 1 square root. And that's it. Now here's the thing, the x to the power 5, I kind of use, again, just for myself, I would look at that as x to the power of 5 over 2. And I know I can yank out 2 x's by themselves, which just leaves me with another x to the power of 1/2, which would be x squared times the square root of x. Now that's just this portion right here. And if that makes sense to you, use it. If not, you're probably going to have to use this stuff until it does. On the other hand, though, on the calculator, if you had typed in 4 times the square root of 24, it would have simplified that for you as 8 times the square root of 6. So you could have gotten this part at least from the calculator, and then you might have had to do some work to get the x's on that. Okay, well, this one, similar idea. We're looking for 28. Let's look at all the factor pairs again. So maybe they'll work, maybe they won't. So I'm looking at 14 times 2. Again, neither of those are perfect squares. You could use 4 and 7, and that's all I can think of right there. Do we have a perfect square? Sure we do. We got 4, which means we're also going to have to use that square root of 7, right? Now again, I'm not concerned about the c to the power of 7. I'm not concerned about that at all because I don't care about it yet. I will get to it though. The square root of 4 is 2, and then the square root of 7, yeah, we can't really simplify that anymore. It's just the square root of 7. Just don't forget this negative 2 that was in the front. That still needs to be multiplied by the 2 there. Now that's the numbers part, and we'll get to that multiplication. But first, let's now go back to the c to the power of 7, square rooted. So instead of writing it as c to the power of 7, I'm going to write it as the square root of 1, 2, 3, 4, 5, 6, 7 c's multiplied together. And now I need pairs of c's that match. There's a set right there. Again, that would be the square root. I'm skipping a step like from last time. I'm just going to say that pulls out as a c, right? Because it's a perfect c squared. Same with the next one as well. This set of c's right there comes out as an individual c. And then the next set as well, these 2 c's pull out as an individual c. Now that leaves us with that last c, which is still in the square root, so it needs to stay there. All those c's are being multiplied, which means that now I've got c to the power of 3 times the square root of c. So that's completely simplified with the c's, and now I can combine stuff. So I got negative 2 times 2, which would be negative 4. And then I'll apply the c to the power of 3, which is on the outside of the root. Then I will apply the square root. So the square root of the 7 and the c, and that is all. Now again, if you typed in negative 2 times the square root of 28 in the calculator, just this, negative 2 times the square root of 28, the calculator would have given you a negative 4 times the square root of 7. That would have simplified that part for you. The c's, though, the calculator won't do the c's. You have to do that on your own. So now, again, I use this method, which is good. So again, for me, I would just do 7 divided by 2 here because our index is a phantom 2. 7 divided by 2 gives you 3 with a remainder of 1. Now, again, I don't know if that helps, but that, with enough experience, that may help you as well, okay? So, first up, again, I don't really care about that 8 on the outside, but I would like to find a factor pair for 24, one of which should be a perfect square, but the biggest perfect square. So, maybe you used 2 and 12, neither of which are perfect squares. 4 and 6 would work. I forgot about 3 and 8, but neither of those are perfect squares either. 5 doesn't work. Yeah, so that's all of them. So which one works on this one? It's the 4 and 6, right? So instead of writing this as the square root of 24, again, I'm splitting it up into its 2 factors of the square root of 4 and the square root of 6. Why? Because the square root of 4 is 2. So then I would have 2 times the square root of 6. And now I can apply that 8 that's on the outside, right? 8 times 2, which would be 16 times the square root of 6. So that's just the numbers part of that. But then we need to focus on the letters. There's 2 letters on this one, so twice the fun. I don't want to write out 8 x's or 9 y's, and if you do, that's fine. So I'm gonna go straight into really what I'm going to use here is the exponent rules stuff, right? So that would be, for example, x to the power of 8. It's the square root. In fact, let's show that part. Square root of x to the power of 8, which is really x to the power of 8, but that square root makes it to the power of 1/2. Now for me, I would just see that as x to the power of 8 divided by 2, which then gives me x to the power of 4. Okay, because we can multiply those 2 exponents, and that x to the power of 4 is legit. It's by itself. It's not in a square root anymore. That has been simplified. Now that's the x's, but then the y's. Again, we're looking for the square root of y to the power of 9. So again, we look at this as y to the power of 9, but that square root right there makes it to the power of 1/2. 1/2. Now, I'm going to show this a little different because that last way that I did it by splitting it up into different exponents like 2/2, you guys hated it, and that's okay. But what I'm going to do now is you can use long division on this. So you can say it's y to the power of, again, I would look at this as 9. I would look at this as 9 divided by 2, long division. And that would be 4 with a remainder of 1. Okay, so why is that important? Because you got 4 with a remainder of 1. That means that you have y to the power of 4. And then the remainder of 1, again, I'm going to show extra steps here, but that'd be y to the power of 1/2 left over, or 4.5, like if you change that to a mixed number. And then that would be y to the power of 4 times the square root of y. Okay, so now I've done all 3 parts on that. So let's start combining stuff. So we got the 16 on the outside, we've got an x to the power of 4, and then I've got my y to the power of 4. Then we got a square root, so we got the 6 inside, and then I've got a y left over, and that's it for this one. So again, if you typed in 8 times the square root of 24, it would have given you 16 times the square root of 6, but the letter stuff you have to do on your own. You're perfectly welcome to expand those 9 y's if you'd like. Again, we've done some of this exponent stuff, so I hope that this isn't so new, or, well, new because we saw it yesterday, but hopefully you feel a little bit more comfortable with this stuff. All right, now on this one, I definitely am not going to want to write 12 x's and 14 y's.
You'd be surprised.
You know, I'm not going to. It's just if it was like 3 or 4 of them, hey, that's fine. One thing we need to remember on this one is that the index here is 4. And that is crucial because the index is 4 means that we need, if you're looking at factor pairs, you need groups of 4. We need a matching, what the heck. Now that's if you use prime factorization on this stuff, which I don't have my my powers of 4 memorized, but my friend here does. So, what we're gonna do here is, again, you can break up the 12 and the 4 and the 14, the exponents of x and y. But let's start with just focus on the numbers first. I don't really care right now about that 3, but I'm looking for factors of 405, right? Let's split that up into 5 times, I will switch that. 81 times 5. Now, yes, 81 is a perfect 4th root, but let's prove it. Okay, so 81 would be the same as 9 times 9, which would split up into 3 times 3, and then this 9 also splits up into 3 times 3. Now those 4 3's right there, so I'm gonna go to exponents so we can get kind of used to that stuff. But now I've got the 4th root, 2 4th roots. One is, I'm gonna show it as 3 to the power of 4, and then the other one, yeah, it's just the 5 right there, right? Why am I showing it as 3 to the power of 4? Because the 4th root and the exponent of 4 undo each other, and you're just left with the 3. So that's 3 times the square root of 5. Oh, yeah, so then I almost forgot there's 3 in the front. So now I will multiply that by that 3. That's the 4th root of 5, by the way. So now I have 3 times 3, which is 9. Times, and that's not, again, it's not 9 to the power of 4, it's 9 times the 4th root of 5. We need to clarify that. But then we've got the x's and y's, right? So we got x to the power of 12. Again, with that exponent of 4 means that I would just take the 12 and divide it by 4. That's nice because it comes out as a whole value of 3. 12 divided by 4 is 3. And then the y as well. So that'd be, dang it, y to the power of 14, but that index of 4 means you divide it by 4. Yeah, so that's going to be y. You're going to get 3 out of that, but then you're going to have a remainder of 2. Now this would be y to the power of 3 times y to the power of, you got 2 remaining, but that's still out of 4. So you can actually simplify that. Now, I'm not going to simplify that. Why? Because I want to keep it inside this fourth root right here. So you would just have to write a separate square root right there. It would not go in the fourth root if you did that. So to make this look pretty, let's start combining some stuff. Okay, so I've got the 9. I also have an x to the power of 3. I can do better than that. So there's a y to the power of 3 as well. And then we'll have a fourth root. The fourth root, and if you want to just clarify that that's a fourth root there and not a power of 34, just throw some multiplication in between that stuff. But I do have the 5, and then I've got the y squared.